Method 1. Evaluation via resubstitution. Okay, so let's move on to evaluating definite integrals using a technique called evaluation via resubstitution. Now, remember in the sections we covered earlier, we mastered the substitution method for finding indefinite integrals, those integrals without specific upper and lower bounds. When we move to definite integrals, integrals with those upper and lower limits, we have a couple of main approaches to deal with those limits during the integration process. This slide introduces the first of those approaches. This method is called evaluation via resubstitution. It's a really useful technique, and many students find it easier to grasp initially. The reason is that it lets you essentially treat the definite integral as if it were an indefinite integral for most of the process. You perform the substitution and integration as you normally would for an indefinite integral, and only at the very last step do you apply those original limits of integration to get your final numerical answer. We'll see how this works step by step in the following slides, but the key takeaway here is that it provides a familiar pathway for solving definite integrals by delaying the application of the limits until the very end. This will become clearer as we work through some examples. Understanding the concept. Okay, let's move on to slide 2. This slide really gets to the heart of why this evaluation via resubstitution method works so well. As we discussed on the previous slide, we're tackling definite integrals using a technique that holds a lot like indefinite integration at first. So, the very core idea here is to first find the general antiderivative of the function inside the integral. Remember, an antiderivative is a function whose derivative is the original function we're integrating. We're not worried about the limits just yet. We're finding the most general function that could have produced the integrand. Now, only after we've found that general antiderivative, do we then apply the boundaries or limits of the integral. These limits, as you recall, define the interval over which we're calculating the area under the curve. A key difference between this method and some others you might encounter is that we don't change the limits of integration when we make our substitution. We keep the original limits, the a and b, in our integral from a to b. This is a really important point to remember, as it simplifies things considerably. Finally, and this is crucial, we return the integrated expression, the antiderivative we found, back to the original variable before we calculate the final numerical value. So, after we integrate with respect to u, we need to substitute back to get everything in terms of x before plugging in our limits. This ensures we're evaluating the antiderivative at the correct points on the original x-axis. Think of this way, we're doing most of the work in a simpler u world, but we always translate back to the x world before getting our final answer. This will become clearer as we work through an example on the next slide, but it's important to grasp this conceptual understanding first. The step-by-step process. Okay, so now we're going to break down exactly how to use this resubstitution method we've been discussing. Remember, from the previous slides, we talked about how this method lets us treat a definite integral almost like an indefinite integral until the very last step. This slide outlines the 4 steps we need to follow, and it's crucial you get these in the right order. Let's start with the general setup. We want to evaluate a definite integral, written as the integral from a to b of a function f of x with respect to x, denoted as integral a to b f of x dx. This is what we're aiming to solve. Now, let's look at the steps. Step 1, temporary substitution. The first thing we do is make a substitution, but temporarily. Notice it says to ignore the limits of integration, a and b, for the moment. This is key. We're simplifying the integral first. We then identify a part of the integrand, that's everything inside the integral sign, to substitute. We often call this part u, and it's represented as a function of x, so we might say u equals g of x. The most important thing here is to make sure that the derivative of whatever you choose for u is also present in the original integral, possibly with a constant multiple. This is because that derivative will become our do, and it will allow us to perform the integration. This substitution transforms the integral into a simpler form, expressed in terms of u instead of x. Step 2, integration. Once we've made the substitution, we perform the integration, but now with respect to our new variable, u. So, we're finding the antiderivative of the simplified integrand in terms of u. Now, a crucial point here, we omit the constant of integration, c. You might be used to adding c when finding indefinite integrals, but we don't need it here. Why? Because when we evaluate the definite integral later, the c terms will always cancel out when we subtract. So, it saves us a step to leave it out. Step 3, resubstitution. This is where we bridge back to the original variable. We replace u with the original expression we defined it as, that is, we substitute g of x back in for u. This brings the antiderivative back into terms of x, which is essential before we can apply the limits of integration. Think of it as undoing the first step, but after we've done the integration. Step 4, final evaluation. Finally, we apply the original limits of integration, a and b, to the expression we got after resubstitution. This is where we finally evaluate the definite integral. We calculate the difference between the value of the antiderivative at the upper limit, b, and the value at the lower limit, a. This is written as f of x evaluated from a to b, which is equal to f of b minus f of a, where f of x represents the antiderivative we found. This difference is the numerical value of the definite integral. So, to recap, the order is always substitute, integrate, resubstitute, and then evaluate. Keep that sequence in mind, and you'll be well on your way to mastering this method. In the next slide, we'll see this all in action with a concrete example. Illustrative example. Okay, let's tackle a concrete example to solidify our understanding of evaluation via resubstitution. As you can see on the slide, we're asked to evaluate the definite integral of 2x times x squared plus 1 cubed, with the limits of integration being from 0 to 1. Now, before we jump into the calculation, it's helpful to understand where this type of integral might show up in real-world applications. The slide points out that in physics, this integral could represent the total work done by a variable force over a distance from x equals 0 to x equals 1, where the force is defined by the function 2x times x squared plus 1 cubed. This isn't crucial for the math itself, but it's good to see how these concepts connect to other areas. Let's begin with step 1, substitution. The key here, as we discussed, is to identify a part of the integrand. That's the function inside the integral, whose derivative is also present. If you look closely, you'll notice that the derivative of x squared plus 1 is indeed 2x, so that's perfect. We'll let u equal x squared plus 1. Then, we differentiate both sides with respect to x. This gives us du over dx equals 2x, which we can rewrite as du equals 2x dx. This is crucial because it allows us to replace parts of the original integral with something in terms of u. Now, let's move on to step 2, integration. We substitute our expressions for u and du into the original integral. Remember, we're temporarily ignoring the limits of integration. So, the integral of x squared plus 1 cubed times 2x dx becomes the integral of u cubed du. Now, this is a straightforward power rule integration. Recall that the integral of u to the power of n is u to the power of n plus 1 divided by n plus 1. Applying this, the integral of u cubed du is u to the power of 4 divided by 4. We don't add a constant of integration, c, at this stage, because, as we discussed, it will cancel out when we evaluate the definite integral. Next up is step 3, resubstitution. This is where we bridge back to our original variable. We replace u with what it originally equaled, x squared plus 1. So, u to the power of 4 divided by 4 becomes x squared plus 1 to the power of 4 divided by 4. Finally, we reach step 4, applying limits. Now we bring back the original limits of integration, 0 and 1. We evaluate our antiderivative at the upper limit, 1, and subtract its value at the lower limit, 0. This is written as the antiderivative, x squared plus 1 to the power of 4 divided by 4, evaluated from 0 to 1. Let's do the calculation. When x equals 1, we have 1 squared plus 1 to the power of 4 divided by 4, which is 2 to the power of 4 divided by 4, or 16 divided by 4. When x equals 0, we have 0 squared plus 1 to the power of 4 divided by 4, which is 1 to the power of 4 divided by 4, or 1 divided by 4. Subtracting these gives us 16 divided by 4 minus 1 divided by 4, which equals 15 divided by 4, or 3.75. And that's our final answer. So remember, the key takeaways from this example are that we kept the original limits throughout the process, resubstitution brought us back to the original variable, and the order of operations is crucial. Substitute, integrate, resubstitute, and then evaluate. Keep these steps in mind, and you'll be well equipped to tackle similar definite integrals. Key takeaways. Okay, let's recap the key takeaways from using the resubstitution method for definite integrals. This slide summarizes the most important things to remember as we move forward, and it'll be particularly helpful when you start tackling more complex problems. First point, independence of limits. This is a really crucial idea. Remember, when we use resubstitution, we ignore the limits of integration, the values a and b, while we're doing the substitution and integration steps. We treat it almost like an indefinite integral at first. The limits stay exactly as they are throughout those initial steps. We only apply them right at the very end, after we've resubstituted back to the original variable. This might seem counterintuitive, but it simplifies things considerably. Next, we have the bridge, resubstitution. Think of resubstitution as the essential link, or the bridge, that connects our work in the simplified world of u, where the integral is easier to solve, back to the original problem expressed in terms of x. We solve the integral with respect to u, and then resubstitution allows us to express the answer back in terms of x before we evaluate using the original limits. Without this step, our answer would be in terms of u, which isn't what we want. Finally, and this is super important, order of operations. Integration isn't something you can just jump into randomly. There's a specific sequence you must follow to get the correct answer. It's first, substitute, choose your u and transform the integral. Second, integrate, solve the integral with respect to u. Third, resubstitute, replace u with your original expression in terms of x. And finally, evaluate, apply the limits, a and b to find the definite integral's numerical value. So remember that order. Substitute, integrate, resubstitute, evaluate. If you follow those steps, you'll be well on your way to mastering this method. Now, let's look at some common mistakes to avoid so you can anticipate potential pitfalls and ensure you're applying this technique correctly. Common mistakes to avoid. Okay, so we've just finished walking through the entire process of evaluation via resubstitution, with a nice example to solidify things. Now, let's talk about some common pitfalls, the mistakes students often make when tackling these types of definite integrals. This slide will help you avoid losing marks unnecessarily. 1. Applying original limits to the new variable. This is extremely common. Remember, when we do substitution, we temporarily switch to working with the variable u. It's tempting, after you've integrated and have an expression in terms of u, to just plug in the original limits, like 0 and 1 from our previous example, directly into that u expression. But that's a big no-no. You must first resubstitute. You need to get everything back in terms of x before you apply those limits. If you don't, you're essentially evaluating the integral of a completely different function. 2. Forgetting to resubstitute. This one is pretty straightforward, but it happens a lot. After you've integrated with respect to u, some students get the antiderivative in terms of u and then stop, or they forget to change back to x before applying the limits of integration. Remember, the whole point of resubstitution is to get back to an expression we can actually evaluate using the original boundaries. It's like doing all the work to build a bridge and then not crossing it. 3. Incorrect differentiation. This is about setting up the substitution correctly in the first place. When you choose your u, say u equals g of x, you need to make sure that the derivative of u with respect to x, which we write as du by dx, is also present in the original integral. And crucially, it needs to match up exactly. Sometimes, you might need to multiply or divide by a constant to make that happen. For example, if your integral has a 2x term, but your du by dx only gives you x, you need to adjust by multiplying du by 2. This ensures that when you make the substitution, everything lines up perfectly for the integration step. So, keep these 3 points in mind as you practice. Avoiding these mistakes will significantly improve your accuracy and confidence when evaluating definite integrals using resubstitution. And remember, the next step after mastering this method is to explore the other approach, changing the limits of integration, which we'll cover next.